开始。
Okay, so for the next talk, we have Xinlu. So Xinlu is a senior student and a senior undergraduate at III's Tsinghua University, and his research interests lie in theoretical computer science with a particular focus on computational complexity theory and the Boolean function analysis. So today, his talk title is Inverse Exponential Correlation Bounds and Extremely Rigid Matrices from a New Randomized X-ray lemma. So let's welcome.
Okay, so thanks, Zhaohua, and thank you for being here. Okay, so tonight the title of my talk is Inverse Exponential Correlation Bounds and Extremely Rigid Matrices from a New Randomized XOR Lemma. This is a joint work with Li Jiechen from MIT. Okay, so let's get started. In this work, we study the computational power of low-degree polynomials. For every integer d, we can define P sub d to be the class of F2 polynomials with degree bounded by d. So in another words, we can say every such polynomial can be written as the following form: XOR of many AND terms. Each term involves at most d variables. So for a Boolean function f, the correlation between f and p is defined as follows, and it measures how well the polynomial can approximate the function. We consider the following well-studied question in complexity theory. Can you find explicit functions f that have low correlation with any low-degree polynomials? So given that low-degree polynomials are ubiquitous in both mathematics and theoretical computer science, this question is clearly interesting in its own right. And meanwhile, the question of correlation bounds is also very closely connected to the study of SE0 parity circuits since the seminal work of Razborov and Smolensky. If you are interested, you can check the partial recent list. Okay, so what's known about this question? Let us review some previous work. First, by probabilistic arguments, we know a random function is at most inverse exponentially correlated with sublinear degree polynomials with high probability. More than 30 years ago, Razborov and Smolensky showed that the majority function on n bits is at most d over square root n correlated with any degree d polynomial, and despite 3 decades past, it is still the strongest correlation bound known for any functions in NP against the log n degree polynomials. And for the higher degree, we do not even know a little order of 1 correlation bound for degree square root n polynomials. So for d less than little order of log n, there are stronger bounds known, but this is not our focus. Since there are not much progress for proving correlation bounds for functions in NP, recently people switched to show correlation bounds for larger complexity classes first. So for example, recently Viola showed a function f that is computable in exponential time with access to an NP oracle. That is the class e to the NP. Case function is at most n to epsilon minus 1 correlated with any n to little order 1 degree polynomial. Here epsilon can be a constant arbitrarily close to 0. And concurrently, Chen and Ren constructed the function f in quasi-polynomial NP time, a quasi-polynomial non-deterministic time that is inverse super polynomially correlated. Their function is at most inverse super polynomially correlated with polylog n degree polynomials. And most recently, Chen, Liu, and Williams constructed functions in e to the NP that is inverse exponentially correlated with any n2 half minus epsilon degree polynomial. Okay, so now we turn to our results. So first, we significantly improve previous bounds. That is, we construct functions in e to the NP that are at most 2 to the minus square root n over log n correlated with any square root n over log n degree polynomials. Here we call e to the NP is exponential time computable with access to an NP oracle. Second, we show there is a barrier to further improve the exponent of our results to any constant larger than 1/2, since it would imply new depth 3 AC0 circuit lower bounds, which beat Hasta's classical lower bounds and would be a huge breakthrough. Lastly, we also consider polynomials with a degree higher than square root n. In this regime, we provide a trade-off result as follows. For every constant beta in 0 to 1, we construct functions that is at most inverse exponentially correlated with degree n2 beta polynomial, and the correlation is increasing as the beta is increasing. Okay, in this work, we also consider the construction of rigid matrices. A matrix M is called rigid if it is far away from any low-rank matrix. Formally, you can define the R rigidity of a given function M as the minimum number of entries you need to change in M to make its rank bounded by R. So explicit construction of rigid matrices with certain rigidity parameters could imply either lower bounds in either arithmetic complexity theory or communication complexity. Due to time limits, we will not go into the discussion here. And let me just show you our new results. We give a new construction of rigid matrices in polynomial time with access to an NP oracle. Our matrix is rigid with such parameters. So roughly speaking, and for our constructed matrix M, unless you change nearly half of all entries, or you cannot drop its rank to be smaller than 2 to the log to 1 minus alpha of n. Here alpha is a constant that can be arbitrarily close to 0. And when alpha is really 0, you can say here is a polynomial in n, which would be very, very good. And we also remark that having rigidity 1 half n squared is the optimal case, since you can imagine that for every 0, 1 matrix, either the O0 matrix or the O1 matrix can approximate it on at least half of all entries, right? Yeah. Okay, so that's our result, and let me show you how we did this. So let's comes to technical part. We first review some previous results and techniques, and discuss the bottleneck of previous approach and our new technical ingredient. Here we study an intermediate model, which we call approximate linear sum of circuits. This model has proven to be very useful by several recent work on showing average case lower bounds from algorithmic method. We will talk about them in a few slides. From now on, let us fix capital C to be an abstract circuit class or function collection. Okay. We define linear sum of capital C circuits. A function L is called the sum of capital C if L can be written as a linear summation of many capital C circuits. The number of subcapital C circuits is called the sparsity of the circuit L. The output of such a circuit is in general a real value and not Boolean. That is not 0, 0, or 1. But we can still study how well it can approximate a Boolean function in the following sense. From now on, let us switch the range of Boolean functions from 0, 1 to minus 1, 1. This is convenient for our purpose, since now you can naturally write the correlation between two Boolean functions as an inner product, like this one. Okay, so for a Boolean function f and a real valued function L, we define their correlation as the inner product of f and L divided by the L4 norm of capital L. The normalizer factor is required, since that you can imagine by multiplying L with a constant, you can make the inner product arbitrarily large. So you need a normalizer factor. The choice of L4 is due to certain technical conditions, and we do not have enough time to explain the details here. Okay, so linear sum of capital C circuits is a useful model, since it can serve as a bridge to achieve strong average case lower bounds from algorithm results. Let me show you the connection. First, following the seminal work of Williams, we know that one can derive sum of C lower bounds by designing non-trivially fast sharp set algorithm for capital C circuits. Then, recent work demonstrated that you can deduce strong average case lower bounds against a class by from a weak lower bounds against the sum of C circuits, following the classical approach called hardness amplification. We will explain these two connections in the following two slides. First, let me show you the first connection. In his seminal work, Williams showed a surprising connection between algorithms and lower bounds. That is, a non-trivially fast circuit analysis algorithm for a class of functions could be used to deduce lower bounds against that class. And recently, this connection was extended to the case of sum of C circuits. Namely, if we can design non-trivially fast sharp-set algorithm for a class of functions, then lower bounds against the sum of capital C follows. Formally, let us define the capital C sharp-set problem. We are given by description circuit C, and we want to compute the summation of C of X over all inputs X. The intuition behind the lower bound is as follows. Recall the sum of capital C circuits is just the linear sum of many capital C circuits. And so we can use linearity of expectation to switch the order of summation and expectation like this one. And then you can assume the sharp-set algorithm for each subcircuit and add the results together. So you know that a sharp-set algorithm for capital C can lead to a sharp-set algorithm for sum of C, and then you can use the standard connection developed by Williams to prove the conclusion. So in general, you have this connection. If we have let Wn be an increasing function, if we can develop 2 to the n over Wn time algorithm for capital C sharp-set, then you can construct the functions in e to the np such that every sum of Wn to 1/4 many capital C circuits fails to 0.99 correlate with F. So you can see that from algorithm result, you can use lower bounds. And so we have explained the first connection, and we go to the next one. Okay, so to make it clear, here we use the notation C sub m to emphasize that we are talking about functions m-bit capital C circuits. So from the first connection, we know that we can construct the function f such that every sum of many capital C circuits fails to correlate with the hard function. And a recent work proved an XOR lemma, showing that XOR independent copies of such a hard function can significantly increase its unpredictability. That is, formally, we define the function f to XOR k, which just takes k independent instances x1 through xk and XOR the f value of them together. We define a new function f to XOR k, and it turns out that f to XOR k is at most 0.99 plus Wn2 minus omega 1 correlated with any capital C circuits. Note that this bound looks very good. It decays exponentially fast with k, and it can achieve a minimum of inverse polynomial in Wn. Here, a crucial advantage of this theorem is that it makes minimum assumptions on the class capital C. Namely, we require it to be closed under restriction and negation. In contrast, previous hardness amplification results usually require the target circuit classes to be closed under taking a majority, which seem much harder to establish. Okay, so now we have all the connections we need to prove some interesting results. So using the lower bounds against the sum of C as a convenient bridge, you can deduce strong average case lower bounds from non-trivial sharp-set algorithm for capital C. Let us apply the general connection to the special case of low-degree F2 polynomials. From a work of Williams, we have a somewhat faster than brute force algorithm for low-degree F2 polynomials. So roughly speaking, when you apply the algorithm to degree D polynomial, you can get a 2 to the omega n over d saving in running time compared to the 2 to the n time brute force. So we set d to square root n and use the first connection. You can construct the function f such that every sum of 2 to the square root n many square root n degree polynomial cannot 0.99 correlate with function f. Okay, this is your intermediate conclusion, and then you do the hardness amplification step with parameter k set to square root n. The new function g, which is f to XOR k, is at most 2 to the minus square root n correlated with any square root n degree polynomial. But however, we emphasize that the function g does not achieve our claim due to the blow-up of the input length. You can observe that the function g has input length L equals n to 3/2, which is considerably larger than that of f. In terms of the new input length L, the correlation bounds and the degree bounds have exponent 1/3 instead of 1/2 as we claimed before. So you can see that when doing the hardness amplification, the increasing of the input length is really expensive. So in this work, we save this square root n blow up during the second step by proving and using a new de-randomized XOR lemma. Our de-randomized XOR lemma is inspired by Impag-Liao's celebrated hardcore theorem. We generalize his idea to a non-Boolean case. So let me do a comparison here. Let us fix f to be a Boolean function, and Impag-Liao's result states that if every majority of n over epsilon squared many capital C circuits L, the correlation between L and F is bounded by 0.99, then there is a subset of all n-bit strings, call it capital H, which is of size omega 2 to the n, such that every capital C, such that f, the function f, restricted to the region H is very hard to predict by every capital C circuit. So this is Impag-Liao's result. In our case, we start from a weaker assumption, that is, for every sum of n over epsilon squared many capital C circuits L, the correlation between F and L is bounded by 0.99. Then there is a function H such that for every capital C circuit C, the correlation between F and H and the correlation between H and the correlation between F and C and the correlation between H and C are epsilon close. So in other words, C cannot distinguish F from H with an epsilon advantage. And also, H has L 4/3 norm bounded by 0.99. It might not be clear from this statement that our result is an analog of Impag-Liao's result. So we can stand Impag-Liao's result in another form. Let us define a function h of x, which is just f of x times the indicator that x is not in H. Okay, so we can state his theorem in this form. You have a function h such that every capital C circuit cannot distinguish f from H, and also H has L1 norm bounded by 0.99. Okay, so here you can see that you can view your function h as the mass you want to subtract from the function f to really get a hard call. Okay, so from this perspective, on the right side, f minus h has a similar condition of being a hard call set. But note that f minus h may not be a Boolean function since h may not be Boolean. So this is why we call our formulation a non-Boolean generalization of hardcore. Hardcore set plays an essential role in de-randomizing XOR lemma, and as application, the celebrated results P equals BPP if E requires exponential circuits. And in our results, we use the non-Boolean hardcore set to prove a de-randomized XOR lemma, and as applications, we obtain the claimed unconditional lower bounds. So this is really surprising since it is unconditional. For the left side, if you want to have the de-randomization results, you need some condition, right? It requires exponential circuit. Okay, so to demonstrate the power of our new notion, we present a new proof of the classical XOR lemma. First, we properly define the non-Boolean hardcore. Let f be a Boolean function. Call h an epsilon delta witness for f if f is epsilon indistinguishable from h by capital C circuits and h has L1 norm bounded by delta. We remark that having an epsilon delta witness implies a correlation bound as follows. If f has an epsilon delta witness, then f is epsilon indistinguishable from a function that is delta close to all zero function, which means that f itself is epsilon plus delta close to all zero function, so which implies a correlation bound. We can now view the classical XOR lemma from a new perspective. The assumption is that every sum of n over epsilon squared many capital C circuits cannot 0.99 correlate with the hard function f. Then the conclusion is there is a function h, which is roughly an epsilon 0.99 hard witness for h. And the XOR lemma states that you can amplify the parameter of the hard witness by doing the XOR. So formally, you define f2 XOR k and h2 XOR k as in this form. And it turns out that h2 XOR k is an order epsilon 0.99 to k witness for f2 XOR k. Let us try to prove the claim. Showing this claim is sufficient to establish these two claims. Claim 1, H2 XOR k has L1 norm bounded by 0.992k. This is straightforward. And claim 2, F2 XOR k and H2 XOR k are order epsilon indistinguishable. This is the harder part. So to begin with, we can write the inner product between F2 XOR k and C as an expectation. And so for every fixed x2 through xk, we consider the inner expectation. And we mark some terms by red color. Let's call this red part D to x2 through xk of x1. This defines an n-bit circuit that cannot distinguish f from h as illustrated in this figure. Note that the function D is just the restriction of C with a possible negation. So the assumed indistinguishability between f and h applies. You can replace the f of x1 by h of x1 by paying a cost of epsilon. And then you can do a hybrid argument and continue this process by paying a cost of 0.99 epsilon. You can replace f of x2 by an h of x2, and then you continue. You do this again and again until finally you reach to the final expectation, the inner product between H2 XOR k and C. And the total cost you pay during this process is bounded by order of epsilon. And this completes the proof. So to wrap up, we have shown that H2 XOR k is a good hard witness for F2 XOR k. And having such a hard witness means F2 XOR k is has a very strong correlation bond. Okay, so now let us try to de-randomize the XOR lemma. The idea is simple. We try to design a pseudo-random instance generator which produce key instances from a much shorter sequence of length s. If we have such a generator, we can define the de-randomized function fderand, and similarly, we can try to define a de-randomized witness hderand. Now, the most technical part of the proof is to construct a generator such that hderand is a sufficiently good generator. hderand is a sufficiently good witness for fderand. That is, you need to establish these two claims. This is the main technical part and the most challenging part in this work, but due to time limits, we cannot cover the details here. So please check our paper if you are interested. Okay, so finally to wrap up, we give new correlation bounds against F2 polynomials in class e to the np. We also give new construction of extremely rigid metrics in class t to the np. To achieve this, we use the algorithmic math framework with our new technical ingredient. That is, we develop a new notion called non-Boolean hardcore set and prove a de-randomized XOR lemma with it. Our framework generalizes classical work by Infagliazzo and Wiggerson, and it might find applications in other questions, since our theorem only requires lower bounds against the linear sum of circuits, and in contrast, the previous Harden's amplification usually requires lower bounds against the majority of circuits, which seem much harder to establish. And thank you for your attention.
Hi, Xin. So thank you for your talk. Can you hear me now?
Yeah.
Yep. And okay, so for myself, I have a general question because I'm not very familiar with the how should I say the process question.
Yeah.
So yep. I see that in your proof, I'm not sure, but I believe that a hybrid method is applied. Yep, in that page. So okay, so and I bet wonder that whether the problem you are studying is relating with cryptography or theoretical cryptography, because
when you hear hybrid arguments, you always imagine crypto, since but what I want to say is that computational complexity and crypto are kind of siblings to each other. I mean, if you study complexity, very likely you also study crypto and vice versa.
Yep.
Yeah, and we share many questions in common, I think. For example, does one-way function exist? Does P equals NP? And yes, so on and so forth. Yeah.
Okay, because when I was hearing your talk and I was also reading your paper, so I believe that is a great work. And okay, and I believe that's all for this talk, and thank you for your participation.
Yeah, thank you for inviting me.
A lot of thanks. Yeah. Bye-bye.
Bye.